Hello everyone, this is Professor Roman. Welcome to the 19th video in my video lecture series, An Introduction to Discrete Mathematics. In this video, I'm going to be in Chapter 4, Combinatorics, Part 1, Elementary Counting Techniques. In this chapter, we're going to begin our study of various techniques for solving what are known as counting problems. And I'm going to give you some examples in a minute. These techniques are part of a branch of mathematics known as combinatorics, and mathematicians who specialize in this field are called combinatorialists. This particular chapter is devoted to the more elementary aspects of counting, and in later chapters we'll consider some more advanced counting techniques. I think the best way to get a feel for counting problems is to consider some examples, which we're going to do next. We will subsequently learn techniques for solving each of these problems. But I think it would be a good idea for now, if you are serious about learning this material, to give some thought now as to how you might solve each of the problems that I'm about to discuss. Also, some of the upcoming examples may seem, well, let's say rather unimportant, and you may be thinking, why would anyone care how to solve this particular problem? And that's a fair thought, but keep in mind that in order to avoid irrelevant matters, I designed the problems in such a way as to keep them as simple as possible. So let's take a look at our first example. In previous days, license plates in California consisted of 3 letters followed by 3 digits. California ran out of license plate numbers and so had to expand the types of license plates they used, but let's just concentrate on this. So our first counting problem is to count the number of possible license plates of this type. And this kind of problem is quite common and appears in many contexts. For example, a certain computer company manufactures computer chips, and they assign chip names that consist of 3 letters followed by 3 digits. I think they assume that something like chip CDX154 is a lot more interesting than chip number 5. So how many chip names are possible? Student IDs at a certain university consist of 2 letters followed by 5 digits. How many student IDs are possible? Next example, a certain collection of 9 books are to be placed on a bookshelf. In how many ways can this be done if the order of the books matters? If sigma is an alphabet of size m, how many words are there over sigma of length n? How many words are there of length at most n? Whoops. Suppose that a bookstore is having a sale on books. You can purchase any 5 books from a collection of 50 books for only $1. How many different choices of 5 books are there? For the next example, take a look at this map. These are blocks. The lines are roads. There are 5 blocks north-south, 6 blocks east-west. We're interested in finding paths from the lower left here, point A, to the upper right, point B, that are as efficient as possible. So every step either takes you to the right or up. You don't go down, you don't go to the left. The bold the bold lines, the dark black lines, give you two different paths from A to B. Question, how many such paths are there? Next example, suppose that your mathematics class has 12 students. On the day that your midterm exams are returned, your professor makes a total mess of things and returns the exams in such a way that no student gets his or her own exam. In how many ways could this happen? Next example, this one's quite important. At a visit to your favorite chocolate store, you decide to customize a 1-pound box of chocolates, which will hold 30 pieces. And of course, you may want to choose more than one piece of some types of chocolates. You might want 3 strawberry creams, 4 English toffees, and so on. So, assuming that all the pieces of the same type are essentially identical, if there's a total of 50 different types of chocolates at the store, in how many ways can you fill your chocolate box? Next example, a game known as the Tower of Hanoi is pictured here in these figures. The first picture is the starting position. The second figure is the ending position. Now, the game consists of a board with 3 pegs, I've just drawn straight line segments here, and 8 concentric rings of decreasing diameter. The object of the game is to move the rings from the first peg to the third peg, according to the following 2 rules. You can only move 1 ring at a time from any peg to any other peg, but you cannot place a larger ring on top of a smaller ring. The problem is to determine, actually, first, whether you can even do this, and second, what is the minimum number of moves required to complete the game. Next example, how many ways are there to make change for a dollar bill using pennies, nickels, dimes, and quarters? So, for example, 5 pennies, 2 dimes, and 3 quarters is $1. 10 pennies, 1 nickel, 6 dimes, and 1 quarter is $1. All of the previous examples I just gave are relatively easy to solve, and you will learn techniques for solving these problems. However, lest you think that counting problems are always easy, there are many simple-sounding counting problems that have not yet been solved. So let me give you some examples. The Coban triangle problem was first dated in 1978 by Koban Fujimura. And it is the problem of determining the maximum number, which I'll denote by K of n, of triangles that can be formed in the plane using n straight lines. So this figure shows you that with 3 lines, the best you can do is get 1 triangle. If all 3 lines go through the same point, you'll get no triangles. 4 lines, the best you can do is 2 triangles. 5 lines, the best you can do is 5 triangles. It's not obvious from the picture in the case of 4 and 5 lines that you can't do better. This is the best you can do. And you might want to spend a few minutes seeing if you can prove that. Currently, the only known values of K of n, this should be K of n, for which the Coban triangle problem has been solved, are for these numbers of lines: 3, 4, 5, 6, 7, 8, 9, 13, 15, and 17. We know the maximum number of triangles you can construct using these numbers of lines. That's all we know. So clearly, we're a long way from a complete solution. Ideas are missing. And the problem was stated in 1978, so it's an old problem. Now, there are some upper bounds that are known for these Koban numbers. A man named Saburo Tamura has shown that the Koban number k of n is less than or equal to the greatest integer in n times n minus 2 over 3. You may be familiar with the greatest integer function. Sometimes it's called the floor. It's simply the largest integer that's less than or equal to the number in the brackets. There was a slight improvement made on this upper bound by two gentlemen who showed that this upper bound can be lowered by 1 when n has the form either 6q or 6q plus 2. So you can see, and this is typical, progress to a complete solution of what apparently is a very difficult counting problem can be painstakingly slow. Let's take a look at one more unsolved problem, one of the most famous unsolved problems in combinatorics. This one has been unsolved for about 95 years. To understand the problem, however, we first need to define a concept that we're going to be using in the future, so it will come up again. And taking a look at this figure here, the complete graph of order n, which is denoted by k sub n, consists of n points drawn in the plane. Those points are called vertices, and the singular of vertices is vertex, together with a line segment, which is called an edge, between each pair of vertices. So K1 is just one point, and there's no lines, no edges. K2 consists of two vertices and the line between them, the edge between them. K3 has three vertices and the three lines, or edges. K4 has four vertices and 6 edges. K5 has 5 vertices, and there are a total of how many? 10 edges, right? Okay. Also, if m is less than or equal to n, and we select m vertices along with their edges from a complete graph, k sub n, what we get is called a k sub m subgraph of k sub n, or sometimes a complete subgraph of k sub n of order m. Let's do some examples, it'll be clear. Here is K5. If we select vertices 1, 3, and 4 along with their edges, we get a K3 subgraph of K5. There are other K3 subgraphs. We choose 3 other points, 3 other vertices. 1, 2, and 5, for example, will give us this K3 here at the top, and so on. Here I have chosen 4 vertices, 2, 3, 4, and 5, along with their edges, and that is a K4 subgraph. You don't have to draw a complete graph that in this symmetric fashion. For K5, for example, you can put the 5 points anywhere you want on the plane and connect them with line segments or curves. It doesn't matter. Okay, so it just looks nice when you do it this way. We will, as I said before, study graphs, both complete and otherwise, in some detail much later in the course. When we're done with counting techniques, we will study what is called graph theory. But for now, this is all you need to know to understand the problem I'm going to explain. What a complete graph is and what a complete subgraph of a complete graph is. Okay, now to the problem at hand. The most popular way to phrase the problem, to explain it to, say, lay people who aren't studying math, is to use the terms friends and strangers, and this is how it goes. Suppose you wish to hold a party, and you want to be certain that no 3 guests at your party are total strangers. None of them have met the other 2. And also that no 3 guests at your party are mutual friends. They all know each other. So those are the requirements for your party. Question is, how many guests can you invite to the party? The maximum number of guests is called a classical Ramsey number, and I'll explain the word Ramsey later. And in this case, it's the Ramsey number of order 3, and it's denoted by R of 3, 3. Okay. This question, how many people can you invite to this party, actually appeared on the United States Mathematical Olympiad quite some time ago, I think. And that's an annual national math contest for pre-university students, high school students basically. One high school student solved this counting problem. I don't know how many others might have. I know that at least one did. So can you? You want to stop this video and see if you can solve the problem? Here's the student's solution. Suppose there are n guests at the party, and denote these guests by the vertices of a complete graph, the k sub n in this case. So there's one vertex for each guest at the party. Color an edge of the complete graph red if the 2 guests that are represented by the vertices are strangers. Color an edge blue if the 2 guests are friends. So this is a partial drawing. It's not the complete graph on 6 vertices. I've just drawn a few of the edges, but there are 6 people at the party in this case. Persons 1 and 2 are strangers, which is why the line between them is red. Persons 2 and 6 are friends. That's why this line is blue. Okay? So that's what we're doing. Color the edges of KN 2 different colors, red and blue, depending on whether the guests involved are strangers or friends. The question before us then can be rephrased. How large can n be? How many vertices can there be without creating either a red triangle, that is to say a red K3 subgraph, or a blue triangle, a blue K3 subgraph? Or in simpler terms, really, how big can n be without creating a monochromatic triangle. Monochromatic means one color. So we've turned this party problem with guests and friends and strangers into a math problem. You have a complete graph Kn. You color the edges either red or blue. You have to color all the edges. How big can n be, avoiding any monochromatic K3 subgraphs or triangles? So that's a problem in graph theory or in combinatorics. This figure, in fact, reveals the high school student's solution. If n is 6 vertices, 6 guests, then draw the vertices and take a look at guest 1. It could be any of the guests, but we'll choose guest 1. There has to be an edge connecting guest 1 with each of the other 5 guests because it's a complete graph. 5 edges, 2 colors. So there must be at least 3 edges emanating from guest 1 that have the same color. Okay. And I've just done an example here that the edges from 1 to 2, 3, and 6 are red. You can't avoid that. It could have been blue, could have been a different set of vertices, but there are going to be 3 edges coming out of vertex 1 that are the same color. Now, as in this example, take a look at 2, 3, and 6. What about the edges between those vertices or guests? Well, none of them can be red because that would create a red triangle, and that's forbidden. Therefore, all 3 of them have to be blue, but then we have a blue triangle. So if we can't have a red triangle and we can't have a blue triangle, we cannot have 6 guests or more. So the maximum number, what we know now is that there can be at most 5 people at the party. We don't know that 5 people is okay yet. Maybe we can't have 5 people either, but that's not too difficult. Here's a picture representing 5 people, 5 vertices. I colored the outside edges red and the, what you might call chords, I guess, blue. No monochromatic triangles. Obviously no red triangle, but if you take 2 blue edges coming from the same point, the 3rd edge is going to be red. So there are no monochromatic triangles, and we have determined that you can have 5 people, but no more than 5 people at the party. So this classical Ramsey number, R33, is equal to 5. And we have a very clever high school student to figure this out. But what if we up the stakes? How many guests are possible at your party if you don't want any 4 guests to be either total strangers or mutual friends? So in graph theory terms, we want to know how large can n be if we forbid any monochromatic K4 subgraphs in Kn. So this is the same problem, except the forbidden graphs are larger than they were. Before they were triangles, monochromatic triangles. Now they're monochromatic K4 subgraphs. I don't think there's a name for those other than K4 subgraphs. This problem, as you might expect, is harder. In fact, much harder. The technique that I just described to you of the high school student will not work in this case. But a couple of pages of detailed mathematics shows that this Ramsey number, R44, now these are 4s because we're forbidding monochromatic 4 subgraphs, K4 subgraphs. This Ramsey number is equal to 18. You can have 18 people, you can't have any more. The general problem of determining the Ramsey numbers RMM, so we're forbidding K sub M subgraphs of one color. This problem is named after a gentleman named Frank Ramsey, who introduced what is now known as Ramsey theory in 1930, 95 years ago. Let's go one step further. What about forbidding monochromatic K5 subgraphs? So that's the Ramsey number R55. Nobody knows. We are stuck at 5. Okay. And nobody knows any larger Ramsey numbers. Let's say I think I used M before, so I'll stick with that. Okay. So that is the state of affairs for classical Ramsey theory. We know very little. A lot of very smart people have worked on this problem. And we're still, very ignorant. This could be one of the most difficult questions in combinatorics, or maybe even in all of mathematics, outstanding unsolved problems. It differs from things like the Riemann hypothesis in that to explain that unsolved problem requires a lot of background in mathematics. To explain the Ramsey numbers does not take much knowledge of mathematics, just understanding points and edges. Okay. Just as an aside, I may not be interested in this, but I am a combinatorialist. I was trained that way. My PhD dissertation was in combinatorics on what is called a problem of Zarnkiewicz. He was a Polish mathematician who first presented the problem. I think it was mid-1950s, 1954, I think. It's not Ramsey theory, but it's sort of a distant cousin. And after I got my PhD, my research for several years was in combinatorics. And then I turned to writing books instead of doing research. I found that more pleasant. I did, however, spend 1 year after getting my PhD, the first year, I had some ideas that were related to the stuff I did for my dissertation to try to determine R of 5, the first Ramsey number that's unknown. Some of the things we do know about Ramsey numbers, as with the Coban triangle problem, are upper bounds for the maximum number. I can't remember anymore, it was so long ago, exactly what the upper bound was at the time I was working on this for R55. But whatever it was, I did manage to bump it down by 1. And I felt pretty good about that. I spent a year working on it, and I wrote a paper, and I decided I'd better talk to some real experts. So I sent the paper to a mathematician named Paul Erdős, whom you may have heard of. He was an extremely famous mathematician. Erdos is his last name. And I happened to know him. And I sent it to Paul, and he wrote back saying, "Congratulations." I also sent the paper to a Hungarian mathematician who was an expert in these fields, Paul Turan, and he wrote back saying, "Congratulations." So I thought it was in good shape. So I sent it in for publication. Unfortunately, some months later, I got a reply from the journal. I think it was Discrete Math was the journal. And they sent it out for review, and one of the reviewers said, "Well, this has already been done. The result, the lower bound was lowered by 1, and the author who did it, the mathematician or statistician who did it, I don't know what he was, published his result in a statistics journal." And I don't look at statistics journals, and I guess neither did Paul Erdős or Paul Turan, unfortunately. So the journal that I sent the paper to said in their letter, well, if you rewrite your paper saying that here is a new technique for getting a result that's already been obtained, we'll publish it. But I was so bummed out by that, especially after the two Pauls had basically said they thought it was a new result, that I foolishly did not rewrite the paper. I went on to work on something else. That was stupid of me. I should have done so, but I didn't. But I have, since then, that was a long time ago, I have advised students or young PhDs, researchers in math, to stay away from problems like this because they're just too hard. And you could spend a year, you could spend 2 years, you could spend a lifetime trying to crack one of these problems and not be able to do it. And then you're in trouble because you don't have a body of work that you've achieved. It's going to be hard to keep a job. So once you are established as a research mathematician, then it may be okay to try to tackle one of these devilishly hard unsolved problems. But I was, excited because I thought I had an idea, and I did have an idea, but unfortunately it wasn't a good enough idea. Okay, I think that's enough for this video. And in the next video, we'll get started on some of those elementary counting techniques I discussed, and it'll help us solve some of these earlier problems. Thank you for watching the video, and I hope to see you in the next video.